Não consegui porque agora se eu tive primeiro, se clicar, eu vou estar muito. Mas eu tenho agora. Eu tenho agora. Não é por causa
Ok, vamos começar, malta. Okay, good morning to everyone. Let's get started. So today is our last class before the exam. Next week, evaluation. But don't stress what with evaluation, that is a little. So today I just have one more part to talk about, theoretical part, which is graphing. I'm just going there. Discuss the architecture of PLCs, ladder programming language, and what we are missing now is okay, no, it's graph. So a graph set can be a programming language, or it can be just a methodology, a conceptual methodology to somehow try to understand better the system that you are supposed to implement and automate. And graph set stands for, well, in English, command graph. I think this is French. Graph, command, etapa, transition. So it's a graph for commanding, transition, and state. Okay, etapa means state. It was originally it was a methodology which was applied to the representation, graphical representation of algorithms used for control centers. So it's a graphical language. It's not really a programming language. It may be, but we are not going to use it as such. We are just going to use the conceptual part. So a graph set diagram has three main things: state, etapas, transition, and action or task. So each state can have actions associated with it. Transition will have what is called receptivity. That's a transition condition, which is associated to the transition. Okay? So a state represents a stage or phase, which is something that takes longer than an instant. So it's something or a state in which the system stays on for a given period of time. And it's a way to split the control procedure into different components. So each component being a state. So the graphical representation is a square, like this. So for example, that's state 18. For each state, you have associated actions, as I told you before. These are the actions, for example, for this state 18. Open valve EAI, turn on motor, start timer, blah, blah, blah. Okay? This kind of action that you already used. For the graph set, you always have what is called an initial state. An initial state is represented like this, with a square, with a double contour. You are seeing my zoom, right? Yeah. Transition. So states are separated between themselves with transition. So transitions are the events that will make the system go from one state to the other. And so the transitions define how the states evolve, how the system evolves throughout the state. For each transition, you have a logical condition associated with it. And this logical condition is called transition condition, or also called receptivity. So in order for you to go from state, in this case it's called E1 because it's in Portuguese, etapa 1, into etapa 2. So suppose that in order for you to go from E1 to E2, what you need is two things. First, you need to be in E1. This is represented by a dot like this. That means you are in E1. And you also need the second thing, which is you need to have your receptivity condition true. Okay? So this is very simple, but it's a formalism. In order for you to go from E1 to E2, you need to be in E1 and to have the transition condition true. And then you do the jump. Between two states, you always have transition, even if it is an automatic transition. For example, you can have this state 1, state 2, and suppose that you are going to go from state 1 to state 2 all the time. So there is no event or no condition in which you shouldn't go directly from state 1 to state 2. You just put here a 1. That means you always go. It's true. A 1 or a 2. So this task that you can see here, these are the actions. They are associated to each state, and they are only executed when the system is in that particular state. Okay. So, for example, if you are in etapa n minus 1, you should be doing actions task n minus 1, and so on and so forth. Sometimes you can have here an action 33, and you can also have here an action 33. So it is possible that two states or more have exactly the same action. That's not a problem. One example is the example from the practical assignment, the last practical assignment, the watering sectors, where you wanted the automatic mode lights always turned on across all the automatic states. So you would have to turn here AGL00, AGL00. So these actions will be the same in all states. So these graph sets are used mainly to represent a sequential operation. So what you need is a system where there should be a sequence of events. First you do this, then if you detect that this is finished, you do that, and then you do a third thing, and so on and so forth. So you should have a sequence of events or states that you want to execute. And then this is already done. Okay, also said that. So this point here, as I told you before, you shouldn't look at this as a replacement of the ladder diagram. Rather, it's a way of thinking about the program, of planning your program, and then to implement this little other in ladder language the code. Okay, so you have different kinds of graph sets. This distinction is actually not very strict or precise. Level 1 graph set, which will give you functional specifications, and level 2 graph set for technological and operation specifications. I really don't know how to give you examples of this. I think this is not very important. This is an example of graphs. So you start with state 0. This is wrong. Actually, this should be like this. Okay. Then initial state. Then you have a transition, which is here, in order for you to go to the state 1. While you are in state 1, so if you are here, then you should be doing action alimentar contributual. That means to feed something. That's the task for an action. Then, once you have the receptivity, which actually detects if the feeding is over, to go from state 1 to state 2, and you are in state 1, you do the jump, and you are now in state 2. And so on and so forth. It always goes from state to state. Nothing special. You've seen it before last week already. So this is an example of a graph set to do control system. So you have outputs, which I always write in red, which is right. That means you activate the car to go to the right. You have left. So this is another output which will tell the car to go to the left. Low is an output where you open a valve and the material goes down. Okay. So what you want? No, again, sensors. You have a pressure sensor, it's like a balance, like scale, yeah, for measuring the weight. You have sensor B, which tells you if the car is in the rightmost position. You have sensor A, which tells you if the car is in the leftmost position. And you have a button to start the cycle. Okay? So your graph set will be something like this. You start in state S1. Then, when someone presses the cycle, you go from being in state S1, you transition to state S2. When you are in state S2, what you want is for the car to go all the way to the right in order for you to be sure that the car is under the stuff that contains the material. Okay, so you want at the end of state S2, or let me say it in another way. In state S2, you just want to be going right, until there will be a point where the car is here, completely to the right. When the car is completely to the right, sensor B will be activated. So when you have sensor B activated and you are in state S2, you transition. Okay? And you transition, you go into state S3. When you are in state S3, you are going to do the action load. Correct. This will open this part here and the material will start dropping. Okay? Now, how much material should you have in the car? This is done by a weight sensor P. This weight sensor P will tell you when enough material has gone in to the car. So when this is true, it means it's heavy enough. So you have the receptivity to go from state 3 to state 4 activated, and therefore you jump from state 3 to state 4. And now you are in state 4. Notice that because you are in state 4, you are not going to load anymore. So the action load is not being carried out. Therefore, the door closes and the material doesn't continue to fall. Then you are going to execute action left, which tells the car to go to the left. So the car starts moving to the left, to the left, to the left, all the way while we are in state S4, until there comes a point where the car is fully loaded on the leftmost side. At that point, sensor A is activated. And so if sensor A is true, and you are in state 4, the receptivity to jump to state 1 is true. So you go back here, and the car stays there, and then until someone pushes the button M again, and you do a new cycle. Okay, so this M is typically the cycle start. This is called cycle start typically. Okay, and by cycle, what we actually mean is sequence. Okay, or auto sequence. So graph sets are to implement automatic sequences of things. Any questions? No? Okay, let's continue. Okay, this is important because in the exam we will have a little bit of this. So transitions are represented by this black square or black cube square, rectangle, sorry. Those are the states, of course, and you can have, for example, when you go here, when you go from S4 to S1, typically you should put an arrow somewhere here to say that you are only going in this direction. Otherwise, someone could interpret this as going from state S1 directly to state S4. But it's not mandatory, but it's better for you to put this oriented arc that we are talking about here. So you should put an arrow when it's dubious. And now you have the convergence and the divergence. Okay, so it can be that you are doing an action, and then you want to implement this action, and then you go to two different states which occur in the same time. Okay, so for that, what you have is it's a divergence. Okay, so suppose that you are here. So this is a non-divergent, and it's represented by these two lines. So if you have two lines, it means and. This is important for the exam. And what it means is that if you are in state S2 and your receptivity condition is true, so if you are in this condition and your receptivity becomes true, what you are going to do, because it is a non-transition, is you are going to transition directly into all the child states. So this, oh sorry. So this will be so this will be here, here, and here. So you are in parallel states at the same time. Okay. Yeah. And later on, you can have a non-convergence, for example, which is something like this. So, for example, now if you are in all states S3, S4, and S5, and your receptivity is true, you can actually go to state S7, let's say. So you go to state S7 because all the previous states, all the states that are parents of S7, you are in those states. So you are in S3 and S4 and S5, and the receptivity is true. So this is the divergent, this is the and convergence, this one. You can also do things alternatively, that's an OR, okay? So let's start again with the NOR divergence. Suppose that you are in state 6. You can actually go either to state S7A, or to state S7B, or to state S17. It depends on the receptivities that you have here. So, for example, if you are in state S6, and this receptivity becomes true, what will happen is that you will do this. So, you go to this state, and because it is an OR divergence, you are not going to be in all the states at the same time, you're just going to be in one, okay? And then you can do the convergence like this. So in this case, you could be here or here or here. Let's call it S3A, S3B, and S3C. And depending on the receptivity, I don't know where you are, but for example, if you are here, you will need this receptivity to be activated in order to transition. Okay? So I'm saying this is important because in the exam I do some exercises like this with the ANDs and OR convergences and divergences. So what are the rules of evolution? I've explained a little bit. Now we are just going to repeat. So rule number 1: at the beginning, you inconditionally, that means all the time, you are going to activate all the states which are defined as initial. So as we begin, we immediately are in state initial, in the initial state. Initial or initial. Initial state or initial state. Then, if the state is active, you are going to signal it with a dot, like I was doing before. So you refer to the state in the transition using this notation. We will see below how this is used. For example, here, rule number 2. A transition is called validated when all the states immediately before the state that we are going to transit to are active. So, what we are saying here is, currently, I'm not in state, so I'm talking about this one on the left. I am not in state 2, so this transition is not valid, right? Now, I am in state 2 because of this dot, so the transition is validated. But still, it's equal to 0, so I'm not going to transit. And finally, when the transition becomes 1, and it was validated, the jump or the transition from one state to the other occurs, and now I'm in state 3, okay? So when the transition is validated and the receptivity is true, transition validated, that means I'm in the previous state. Receptivity means the transition condition is true. It's mandatory by the rules of the graph set evolution that the transition occurs. You cannot say, oh, no, I don't feel like, so now I'm not going to transit. So you always transit under this condition. Rule number 3. So when you do a transition, you are going to activate all immediately following states at the same time that you deactivate the preceding one. So, for example, this is an AND, remember? So this is an AND. Why? Because we have a single condition. So we need to be, we have a validated condition. Right now we don't, because we are in giving 5 and we are in 5, but we are not in 4. So it's not true that all the preceding states are active. Therefore, the condition is not valid. From the moment where I'm in states 4, 5, and 6 at the same time, my transition is going to be valid. Okay? And when I have my receptivity to true, I'm going to transit from state 4, 5, 6 into state 7, 8. So I'm going to activate all the immediately the next state. That's why I activate 7 and 8. And I'm going to deactivate all the preceding ones. That's why we are not in states 4, 5, and 6. Okay? Rule number 4. So you can validate several transitions simultaneously. So, okay, so this is when something occurs simultaneously. So if you have simultaneous validation and receptivities, you also do the transition simultaneously. Now, at some point, and we will show an example below, because the way the graph is done, you can both deactivate and activate a given state. In that case, the state remains active. Okay, the activation wins. This is another example. So in this case, the transition is not validated because we are not in state S4. When we are both in state S4 and 12, 4 and 12, the transition is validated. And finally, when we have our receptivity turned true, and because the transition was validated, we have the transition, the actual transition being done, being carried out, and we are going to go into state S7 and go out of state S4 and 12. Okay, here's an example of the simultaneous transposition. So let's say that we are in state S4 and 12, and we have two conditions here, two receptivities, but they have the same logical equation, which is E2, this variable. So once E2 becomes active, that means that both this transition as well as this will become possible exactly at the same time. And therefore, you are going to simultaneously carry out the transition. That's why you went from state 4 and 12 to 7, and from state 12 to 9 and 7. Okay. So this the example that I told you before. What if you want to activate and also deactivate a state? This is the example. So again, we here have the validated condition. We are in state 4 and 12, and we should go into state 7, but also into state 12 again, okay? Because of this. So once E2 is true, we have to go into 7. So we go from 4 and 12 into 7. That's normal. But also we have to go from 4 and 12 back to 12. Okay? So because of this, 12 should be turned on. But at the same time, because I'm moving from 4 and 12 to the next state, 4 and 12 should be also turned off. So in this case, 12 should be off, but it also should be on. Okay, when this occurs, the state continues on. So the activation limit. Did you understand, Gonçalo? You are facing you? Sim? Isso foi para o cara que não está. Ou então está pensando outra coisa. Está pensando no jogo de futebol, né? Okay, don't worry about this. Microstates, I've never used them before. It's just a way of having hierarchical graph sets. So basically, you can have here a state which encapsulates another complete graph set inside it. Okay, it's just a way to do a hierarchy, but we are not going to use this. This is just curiosity. Also, subroutines, they are more or less the same as macro state. So also we are not going to use them, so don't worry a lot about it. Just know that if you go and work in automation, probably you will need more complex structures, and these graph sets also accommodate for that if you need. So you can have functions, you can have macros. I didn't use them. Now for the action. So we are always going to use this representation. So this is the representation we use. This is the state. Well, not this, actually, not this representation. Yeah, this. Let's use this because that's the one that comes out in the exam. So you can have this representation where here you have some kind of modifier. I'm going to call it modifier. This is the action. Or the description, actually. This here is the description. And this here is the action. So the description is just that. I'm going to start watering sector 1. This is the description. The action is the valve, turning on the valve that actually starts watering sector 1. YV01. And the modifier is like your keyboard modifier keys. You know which are the modifier keys? These are the Alt, the Shift, the Control. These are keys where, for example, if you press A, you will type small a. Whereas if you type Shift A, you will type a capital A. So the Shift is actually modifying the functionality of pressing A. Also for the Alt and for the Control, this kind of stuff. So this placed here, number 1, will be used to modify not the presses, but the action. Okay, so you can actually modify the way the actions are carried out by putting some kind of symbol there. These are the symbols. So you can put C for a conditioned action. D for a delayed action, L for a action limited in time. These two are very similar to the T on and the T off, something like this. Okay, similar, not the same exactly, but similar. P for a false action, and S for a set or memorized action. We will see examples. Often we can also show this. This is a very simple example where we don't have number one is hidden. Number two is also hidden. You just say webinar, that's you only are putting number three. So it's as if you don't show number one and two, you just show number three. We don't do it like this. Typically, we do it like this, okay? So, for example, here, this is an example of a conditional action. So you have an action. The action is aquecer. This is like turning on a heater. And when you are in state one, you are going to aquecer only if, because this is the conditional action, so the action is dependent upon the condition, the thermostat, which is the center, something like this, temperature center, okay? So basically what you mean is you are going to heat if the center thermostat is on. You can put them, you can write them in these two ways. Either you put the condition there, or you just explain how you're going to use the condition in the distribution, okay? A delayed action is an action that will start only after some time. So let's say that you are in state one. You are here. And now your receptivity is true. Once it happens, again, you are going to go into state two. In state two, you are supposed to do the action close. This is your action. But because you have a delay modifier, you are not going to immediately start closing. You are in state one. Let's say this is state one. Then you go into state two. And when you go from state one to state two, you are not going to immediately start closing. You are going to wait a little bit, and then you are going to start closing. Okay, and this time here is what we have here, 0.5 seconds, okay? So D delays the start of the action. So the action will be not immediately executed upon entering the state, but there will be some time before the action starts. A limited action is more or less the inverse. So basically, in the limited action, what happens is that when you enter the state, you immediately activate your output. That means that siren here will be immediately turned on once you enter state 3. But this action will only last for 2 seconds. So, for example, if you are in state 2 and now in state 3, when you transition to state 3, your action will be off while you are in state 2. It will turn on when you are in state 3, but then, even though you remain in state 3, it will go down. So this is the action siren, which is like a buzzer. Thank you. Okay, and this time here that you have your output on is 2 seconds. If you have questions, let me know. You are very quiet. So a false action is like this. So again, you are in state S3, and now you're going to move to state S4. So when you transition from state S3 into S4, your activate output, so this is activate, this is just an output, is going to be activated with a pulse. What is a pulse? It's just being turned on for a single instant in time and then immediately again going off. Okay, so it's just a pulse. Okay. By the way, this sign here is the PLC is one PLC cycle, which is around 10 milliseconds. We've learned before. Okay, memorize action. These are a bit more tricky, so you can represent them like this. So S stands for step. And what we're doing here, if this is more or less similar to the, again, not exactly the same, don't be confused, to the set and the reset in the ladder language. So when you set a variable, the variable will be true until you reset it. That example that I told you of throwing something up in the air in orbit, it will be there, up there, until you bring it down. So here, when you are in state 6, so let's say that you are here in state S6, then here in state S7, then here in state S8. So what will happen here for your XDR output is that when you are in state 6, it will be on. This is 0, this is 1, this is 1, this is 0, so it's on. Then, because you did a set, it is going to be on until it's turned on. So during state 7, it's still on. And then when you went to state 8, it's turned off. So only here it's turned off. Okay. So let me show you the difference to a regular variable. So, for example, if you have here something like out, okay, what will happen here? You have your out turned on while you are in state 6, and then immediately when you go into state 7, because you don't turn on out, it's going to be off. Okay, yeah.
Can we use the letter R, or will you choose the S, or choose 0? Like R for reset, or reset?
No, I think it's only yes. Look, at least from here, there is only an S. I don't know if you can use the R.
I think you can use the R or reset.
Okay, so perhaps you can. But don't count on it for the exam, okay? Count on this formula. So you can have several actions. You don't need just one action. We've done this before. So in our example from last week, in a given action, we would be watering sector 1 and turning on the automatic globe lamp or lights, so LED. So this is nothing new for you. So you can have more than one modifier. And for example, in this case, you are going to delay for 6 seconds, and you are going to do a set. So the action to read will be set to 1. In this example, you are going to do the set of the output of read only if your condition is thermostat equal to true. Okay? So you can combine several modifiers as you think, if you want, if you need. So let me see. Now we just have some examples. I'm just trying to figure out. Okay, let's look into this example to start. So we are going to simulate a conveyor which is going to feed the press. And we are going to have the following inputs. So you have input E0, which is turned on. So when you press E0, the conveyor starts moving. This is the output S0. Then the system has a sensor called E1, which says that there is a part in the proper place. Then 10 seconds after E1 is active, the conveyor will stop and the press will go down. So for the press to go down, you need to activate S1. The position of the press is detected by another sensor. So this is another sensor. E2, which detects if the press is down. And when the machine is turned off, the cycle should be executed until the end. Okay. So these are our inputs, the E's, and these are our outputs, the S's. So this is okay. So how can you do this? So we are going to start. This is the initial state. We call it the start state here. Then, when someone presses E0, we should start doing the second state. Okay. The second state should be, I think, lower the press. Okay. No. That's start the conveyor. Yeah. Start conveyor or move conveyor. Okay. Move. So we are going to start moving the conveyor. We are going to keep on moving the conveyor until we reach a time where a part is detected. This is the part E1. Okay. So when we have E1, this is cycle start. This C1 here is the part detected. So when our part is detected, we are going to move into the second state, which we here call step 3, which activates F0 still. So we continue to move the conveyor. And we start a timer. We call it timer 10. Okay, because it's supposed to be 10 seconds. Once the receptivity is pin 10, that means 10 seconds have passed since you start the timer 10, we are going to step S4. Step S4 should be, let's go back here, to lower the press. Okay, so I think we are now in linear data. So now we are going to start lowering the press. Lowering the press is S1. So we should be activating S1. Here we are. So this is lower press. And so now the press is coming down and down and down and down. When do we know that the press has finished, has gone all the way down? When center E2, which detects if the press is down, is active. So once this happens, you know the press is all the way down, so you can go into step 5, and in step 5, a ordem a princípio, okay, this is it. A ordem a princípio voluntária é como instrumento. So in step 5, we should put the conveyor back to operation, back moving. So that's why we are activating this conveyor. Diga, Bruno.
No, I think in this case, you stop the conveyor, because we stop each conveyor.
You are talking about step 5?
Yeah.
And you say you should stop the conveyor? Why? Because look at the Portuguese here. It said,
okay, but when we stop the conveyor in purchase, turn one of them.
So we stop the conveyor when we are not activating X0, that means during step 4. That's the only time where the conveyor is not moving because the press is coming down. Make sense? A pessoa que está aí com dúvidas, diga-me se claro, certo, estamos aqui a dar uma coisa. Qual é a sua dúvida, Bruno?
Não, eu só não entendi quando que a gente parou a coisa.
Quando é que a gente parou o texto?
A esteira.
O conveyor. Parou. Então, você mexe quando ativa o X0.
Sim.
Então parou quando não estava numa ação. E o único que quando o X0 não está com uma ação é no step 4.
Tá, entendi. Não é o 7. Vai entender.
Não há. Se tivesse feito S0 igual a 1, aí sim estava sempre ligado.
Sim. Sim. Não é isso. Ligado.
Não tem mais uma coisa.
Só no step 4, vai parar no step 4. E depois vai continuar, porque no step 2 é MOX.
No step 3 também?
No step 2 também, no step 4 é para mais já. E no step 5 volta.
Exatamente. Está sempre a mexer, exceto no step 4. E no start. O que é que eu fiz aqui? Às vezes acontece, Ok. Continuing. So this was the first example. It says here, do the necessary changes to the graph set so that the timing occurs, so that there is a timing between. Okay, what can happen? So now, the conveyor is moving, I'm going to represent by this. Then you are in step 3, so the conveyor is moving for 10 seconds. Once these 10 seconds finish, you stop the conveyor and you start putting the press down. Now the press goes all the way down, it reaches the bottom once E2 is activated, and then you jump immediately to step 5. So the press starts coming down because you are not activating S1, but you activate S0, so immediately the conveyor starts moving. So in this instance, when the press is coming up and the conveyor starts moving, you can have some interference here where the press is not completely, there is not enough clearance for the press, so the press is not up enough for the conveyor to start moving. Do you understand what could happen here? So what they are asking is for us to do a change so that before we put the conveyor back to work, we actually wait for 5 seconds. So I would say that we can do something like this. We do a new state. Let's call it step 4.5, which is in the middle. So the transition from step 4 to step 4.5 is the same, so the press is down. Step 4.5 will start timing. Timer 5 seconds, and then there will be a transition here, which is steam 5. So once that 5 seconds finish, you go into step 5, and only in step 5 you start moving the conveyor. Make sense? So that's it. So in this case, we have traffic light, and the idea is to control with the following rule, okay? So the rules are the following. Sorry. Next time you put it in. Okay, you should assume. No, I don't have anything. Yeah. You can. Really? You're passing my phone. No, if I can. Não sei.
Não é o segundo aí, para contar da sugestão.
Eu vou ter.
Depois tem que fazer isso.
Foi, mas não consigo, é mal tentativa. Copy, tem agora o preço, imagina. É que agora está aqui copy verde.
Só serve para
Depois que não começo que era.
Não faz?
Sim, depois nos 3 pontos, se calhar pode estar lá nos 3 pontos mesmo. Não, os 3 pontos, viu? Ao lado da outra.
Não.
Não.
Não sei, é a ideia de Miguel ainda. Ok?
Minha peça, eu faço selecionar e depois perguntando aqui para.
Espera lá, agora. Então, tenho este também. Então, agora eu posso fazer assim, que é. Tenho também que ter lugar do outro. Agora tenho 2, não é? Isso. Agora quero este. Este é para o. Este é 5 e agora quero 4. Pronto. Agora tenho que esperar para o sítio, que eu já não sei onde é que está. Aqui, pronto, agora sim, temos aqui isto deste lado e deste lado. So, okay, now we have the text on the right-hand side and we do our graph set on the left-hand side. So, inputs, we have the following inputs. We have input E0, which is when, so this is for a traffic light control, the control of a traffic light in a row, in a street somewhere. So basically, E0 is for a person to press the button to say, I want to go to the crosswalk. Then S0 is an output. It says it's red for the pedestrian. S1 means it's green for the pedestrian. S1B is also an output which says intermittent green for the pedestrian. And then S2, red for vehicles, S3, yellow for vehicles, S4, green for vehicles. Okay? So, how can we do this? Here's the example. So, once we are in the start state, so when we are in the initial state, I would say that we allow cars to pass. So we have the green for the car and the red for the pedestrian. That makes sense, right? Now, when a pedestrian starts pressing E0 and says, I want to pass the crosswalk, so when this is true, E0, we are going to move into step 2. So when we are in step 2, the system is actually going to start to tell the car to stop, and only then allow the pedestrian to cross. So we continue to say to the pedestrian, you cannot pass. So to the pedestrian, the red continues. And for the car, we start the yellow light. For the cars that are coming to start slowing down. Or in Portuguese, in Portugal, and also in Italy to speed up, right? When you have a yellow, you speed up fast in the traffic light. Yeah. Then, okay, so we put the yellow, and we start a timer for 3 seconds. So this is just 3 seconds. Once the 3 seconds elapse, we go into the next state. So what we say here in this state is, we assume that we've shown enough yellow for the cars, so we turn on the red for the cars. Sorry, the red for the cars is the second one, but we still continue to turn on the red for the pedestrian. And we count again 3 seconds. So when the 3 seconds elapse, we are going to step 4. In step 4, finally, we are going to put the green for the pedestrian, and of course, we put the red for the car. And we give the pedestrian 10 seconds to cross. So we start counting 10 seconds. Once this 10 seconds elapse, we go into the next state, which is here, where we are going to warn the pedestrian that the green is going to be over. So we continue to say to the car that they cannot pass, so we put them red, and we start with the intermittent green for the pedestrian. That's when the green starts blinking. And we count 5 seconds. Finally, after these 5 seconds, we go into step 6, where we are going to say that the car is red and the pedestrian is also red. So nobody can pass for 3 seconds. And then, okay, then this is when 3 seconds elapse. And of course, we should have here an arrow just to say that this is the only possible direction. We go back to the start where cars are allowed and pedestrians are not. Make sense? Nothing special. Okay. So I think this is very easy. This is an exercise for the exam 2 years ago or something. So there will be 2, 3, 4 questions about graph sets in the exam, and these are the kind of questions. So can you try to help me? Well, which one you think is true? Let me just take this one away. Yeah. So which one? Again, this is a graph set. and you have conditioned action, you have divergences and convergences, and so you have here a set, we have here a pulse, we have here a timer, we have here a latch. That means only for a couple of seconds. So my question is, would you be able to answer this? Which one do you think is true? So the question is, the output A0 in the graph set, and now you have to select which option is true. The first is on whenever you want to state S0. Is on for approximately 5 seconds. None of the others is on in S0 and off in S1. Is always at 1. Is always on. Always on. Why? Yes, because well, not. We know if you are right, but it's correct but incomplete. Why? Because if you set it and never again reset it, for it to be always on, you also have to say the second thing, which is and reset it at the beginning. Right? So you set it in the initial state and then you never reset it again. So that's why it's always yeah, right. And so another question: how long does it go? How long do you have? So suppose that you start in S0, and then you go to all the states and you go back to S0. On the first iteration, how long do you take?
10 seconds.
How long?
8 seconds.
8 seconds, says Gonzalo. Gonzalo, sorry. 8 seconds. Any other suggestion? 6, who said it?
16.
16, Gonzalo, right? 16 seconds. Okay, any more opinions?
The latch delay is the right.
No, that's the D. Delayed latch, you'll activate for that time, then never again, and then the active. It's yeah. You want to see the yeah? I will show. Well, I don't want to take this away for the people to take a look at. So, any other opinions? No. So let me see. I don't remember. So, okay, no opinions. Do you agree with Gonzalo number 1 or Gonzalo number 2? Gonzalo number 1. Okay, 1 vote here. Any more? Says it goes to 3. Okay, another vote there. Okay, so let's see. Gonzalo, can you explain how you thought?
So
we are in S0. Now what happens?
no, it goes to S1 when SP1 is good.
Okay, so let's see. Let's say that SP1. Well, there was something missing here. Let's say that immediately I press SP1. Okay, so SP1 is pressed immediately. So yeah, so you jump here and you spend 0 seconds. Then
we'll go to the next step after 5 seconds.
So you go and do you go to S2A or S2B? Both. You go to both.
Yes.
And you spend 5 seconds. Okay. Now what happens?
Oh, yeah, it will start both timers, but it yes, and for both timers as 3 seconds.
Wait, there's something here that I missed.
So,
Yeah, there's something missing. Oh, come on. How come you yeah. So now you again, can we say?
no, in S2A, will delay 3 seconds.
So we are going to wait 3 seconds?
Yes.
Not really, no. So the action will be huh?
The D is the
That-
TR.
Yeah, so but yeah, but you are confusing things like this. Look. You are here in S1. Actually, this is 5 seconds, okay? Then you are going to be here in S2A and S2B. So you are in this state, but what happens is that you are going to delay YD1. So you are going to put 3 seconds, and then you are going to turn on YD1. But if you are in this state S2A and S2B, for example, for only 1 second, so if this is 1 second, you are never going to turn on YD1. Make sense? So you delay the action, but if the state does not exist for long enough for the delayed action to start, it never starts.
But the step says we will stay there for 3 seconds.
Yes, in this case, yes. Okay, I'm just saying, yeah.
The other two.
So for because okay, let me say like this. Because of this, you wait 3 seconds, not because of the other. Okay. So because of this, you wait 3 seconds, and then you move on to state S3, right? Let me go back to this. So this, and you jump after 3 seconds, you said?
Yeah.
Yeah. How about SP2? You don't care about SP2?
It's another button there.
Yeah. Well, I forgot because during the exam, so this is the question for the other, this is the text for the other question. For a question similar to this, I have to say how long does it take to press SP1, or if SP1 is always on, and how long does it take to press SP2? So this is going to be 3 seconds, or SP2 if SP2 or SP2 or sorry, this is 3 seconds or the time to press SP2 if more than 3 seconds. Make sense? So suppose there is an operator there. If the operator waits for 10 seconds before, since you go into S2B, sorry. When you enter this, it is going to wait 10 seconds and only then press, you are going to wait for 10 seconds, right?
So it's at least 3 seconds.
Sorry?
It's at least 3 seconds.
At least 3 seconds, yeah, exactly. At most, the time that the operator decides to press SP2. And then, so, but okay, let's say that SP2 is always on. So if it was always on, yes, you have here these 3 seconds. And then, how long do you stay in S3? So you need to activate this output in a delayed action. How long do you stay there?
So, like, immediately, it has.
Yeah, because the transition, so the transition is, the condition is validated, and you have receptivity always true. So you only spend an instant in S3 and immediately you go away. So there you spend 0 seconds. So 0 plus 5 plus 3 plus 0 is the 8 seconds that you said, right? Makes sense.
So the when you here will never turn on, right? Because you
The what are you doing?
the why you change here the
Will never turn on.
because we spend less than 8 seconds to come here again.
I think it will turn on for a pulse because you are going during one cycle of the PLC, you are going to be in S3. And during that cycle, YD2 will be on. The next cycle, you are going to transition to S3. So, Gonçalo, wait. How did you say 16 seconds?
So it's started on the S3 8 seconds.
Ah, okay. So you fall into one of the traps. So there will be more traps like this, and you just have to do this kind of reasoning for next week. Okay, you have to try to understand. To answer these questions, these are the kind of questions that I ask. Okay, that's it. Any questions about the graph set? No. Okay, 10 minutes break, and then we go back. We go to the practical assignment. Okay. Okay. You don't do. O que é que se passa? Ninguém quer ir lanchar? Ah, boa. Sim, ligar-te a porta primeiro. Boa ideia. É verdade, já há licenças? Ainda não? Pois, é amanhã. Amanhã. Mas é assim, se for é em inglês. So we are having problems with the Via Portal license. They didn't fix it yet. So if all goes wrong and we do not have licensing, what I will do is I will evaluate the program for the practical assignment in your computers in the simulation. So it's not your fault that there are no licenses here, okay? And I will ask again, but let's see what they say. I will ask again to see if they give us license. In any case, try to do everything working on simulation, and then hopefully we will have a license. You can also try to pass directly the code from your computer to the PLC. If you have a connection for net and cable, nobody has a connection for it. Pois, mas e vocês têm de ligar? So I have a dongle like this. I have a dongle which allows me to connect to Ethernet like this. Yeah? So this is a USB 3, USB-C to Ethernet. You can have one. I can give you one of these, but I only have one. No problem. So we can try this. If you have everything working on simulation, I will give you this to try. Mas se não chegar a isso, vamos comprar coisas destas. Acho que não tem. Mas por isso é que eu estou a dizer que se calhar devemos comprar.
Se nós não tivermos nada a fazer, ela peça uma saída. As novas configurações, depois daquele lado, de alguma maneira, pôr da maneira que o professor quer. A própria maneira que eu chego. Consigo fazer consigo no formato, é isso que está na pouca coisa. Pois, eu tive a categoria, não está em campanha. E não há tudo.
Eu tinha visto, deve ter ideia, mas também ficou igual. Não tem que ficar igual. Eu já fui.
O professor disse, com este formato, não tem aquele formato. Acho que quando não tem o e pode apostar nos. Ou seja, pode estar na primeira.
Hey, good morning.
Okay, so to compare this, so I'm say that again. Well, say this.
So, for this one part, the time is yours, continue to work on this side, and we'll call you when it's okay. Think.